Our next speaker is David Sims, and he's going to talk about a new power module package for electric and hybrid vehicles.
Thank you, Mike. Okay, so I am a commercialization manager here, and the principal investigators of this particular technology are Laura Marlino and Jinxing Liang. They're both in the back of the room today, so for any technical questions, I'll be deferring those to them. All right, let's see if I can work both of these at one time. Obvious? Yeah. Okay, so just to give you kind of a conceptual picture of what I'm going to be talking about, the power electronics in this particular graphic here are right in this area. So the power electronic systems in this particular representation of a plug-in hybrid vehicle exist in that space under the hood. So power electronic systems include both power modules, which are comprised of the power semiconductor devices and the packaging components. The power module packaging provides electrical interconnections, thermal management, and mechanical support for the semiconductor devices. You can kind of think of the packaging as the ins and outs and the protection for the electronics. So conventional power electronic systems, which are from industrial motor drives. So here's an example of a conventional power electronics package there. Those are problematic because they come from industrial motor drives. They're not really designed to work in these terrible environments that you find in electric and in hybrid electric vehicles. You've got high heat issues to deal with. You've got dirt, you've got vibration, you've got humidity. If you know anything about electronics, you know that none of that is good for electronics. So due to the low demand for electric vehicles and the hybrid electric vehicles, the commercial manufacturers really haven't put a lot of focus on the R&D aspects of power electronics. But as demand has started increasing, now more attention is being focused on cost, reliability, functionability, power density, and efficiency of the power electronics. So to give you some idea of what we're talking about here on cost, an electronic module would cost about $600. The packaging of it could cost up to about $300, so about half the price of a power module. In electric and hybrid electric vehicles, just ballpark, there's about 7 additional modules in these automobiles. So in the lower part here, this would be the conventional packaging or power electronic module here. So what you've got on the bottom is the heat exchanger, and the power electronics sits right up in here, connected by this wire bond. Our technology, which is up at the top here, and that's a quarter right there, so you can, well, let me just show you. So existing conventional power electronics and our technology. Big difference in size. So in the conventional modules, you've got the issues that we have to deal with here for electric and hybrid electric vehicles. Electrical interconnection, the thermal management. As you go to the right here, what all that translates to is issues related to cost, reliability, efficiency, and density. So, so our technology has two heat exchangers, one on top, one on bottom, and in between is sandwiched the power electronics. What's also kind of interesting about this, it's considered 3D architecture. So rather than just the power flowing on an X, Y type axis, it actually adds a Z axis. So you kind of get this flow that's going through the module, which that's important because you get increased efficiency here. So current stage of development is a TRL-7, which is fairly high. It's been tested in a 200C environment, which translates to about a 400 degree Fahrenheit environment. The conventional module, as I said a while ago, it runs about $600, conventional packaging up to $300. The ORNL package is about $200. However, because you can put fewer semiconductors in the same power rated module, when you apply the ORNL package to the overall module, the price actually drops down to $400. So you can quickly see that you get $200 worth of savings if you've got 7 modules in these hybrid electric vehicles. You can get $1,400 worth of savings right off the bat. And there are other power modules in cars. I mentioned the ballpark 7 because that's what's added with electric and hybrid electric vehicles. So it's ready. It's about 6 months away from being ready to commercialize and put into a production environment. And that is if you're applying this to the current silicon chips. What's left to do on that is the reliability testing. It's about 1 year to 1.5 years away from production, ready for production, if you're talking about applying this to wide bandgap technologies. The intellectual property we have is U.S. patent application, and we have both apparatus and method of manufacture claims. You can also apply this in areas of photovoltaics, wind energy, data centers, industrial power drives, but the biggest market is the electric vehicle and hybrid vehicle market. So why is this unique? It eliminates the major deficiencies that exist in commercial modules. It reduces manufacturing steps, it eliminates wire bonds, it enables the double-sided cooling to take place, and it strengthens the mechanical properties. Below this, I've listed out the performance indicators that show that this works as anticipated. I'll just highlight the manufacturing steps. So this is a fairly easy manufacturing process. I'm going to pass this around. So it drops from 7 to 3 steps, and basically the 3 steps are: you take a fixture and you put the components into the fixture. This is on a conveyor belt system, so it runs through step 2, which would be the kiln, to heat it up, bake it basically. And then the third, coming out of the kiln, the third process would be to apply the epoxy to bond it together. So I'll just pass this around so you can see it. Okay, so as I mentioned a while ago, if you want to apply this to silicon chips, the existing silicon chips, what we're looking at is we need to have feasibility or reliability testing done. That'll take about 6 months to do at a cost of about $250,000. To move into the wide bandgap applications, there needs to be material testing, testing of the materials and the bonding compounds, and also reliability testing on this. That is probably going to take about a year to do, cost about $375,000. These are ORNL prices. If ORNL was going to do the testing and development, this is what it would ballpark what it would cost. The challenges to overcome are going to be in the high temperature materials area and getting the efficient manufacturing processes in place. So one way, different ways you could go about commercializing this. One way is, first thing you want to do is option the patent application. what you would really, because we're talking about automotive applications here, you would want to investigate partnerships with existing suppliers. Getting into the automotive industry is tough. So you would want to investigate that. You would want to complete the reliability testing and the other R&D that needs to take place. If you decide this is a go, you might consider building the manufacturing facility here in East Tennessee. It takes advantage of the close proximity to ORNL and to UT, as well as there's financial incentives from the state of Tennessee to get automotive-related manufacturing facilities going. It's certainly appropriate for a startup. I consider this to be a disruptive technology. To get a manufacturing startup going, we're talking about somewhere between $3.5 to $4 million for equipment, operations, for a staff of about 3 to 5 for 2 years to get it up to production scale. Once it's at that scale, we believe that you could supply up to 15% of the market at that level. So here's an example here that we got from some marketing research as well as the inventors of some potential commercialization partners, tier 1, tier 2 suppliers. Obviously, it would be good to hook up with tier 1 suppliers, but tier 2 would work well as well. So here is a competitive differentiation chart. I've talked about the parts of it that we think make our technology superior. The only one we're not sure of is this reliability testing and the high temperature bonding. To give you some idea of the market, at least one company has estimated that by 2020, the power module market, you're looking at about $50 billion. About $30 billion of that is for electric vehicle and hybrid electric vehicle. So to wrap this up, this is a new electronics packaging that helps achieve DOE's U.S. Drive technology targets. U.S. Drive has the Detroit 3 auto manufacturers as well as Tesla, so they've bought into this already. It's at TRL7, very high technology readiness level. It's disruptive technology. It provides an entry into the automotive industry, which is growing in Tennessee. It's automotive-related manufacturing, so the possibility of state of Tennessee funding incentives are there. You've got several applications beyond automotive that this could apply to, and you could enter into the market within 1 to 2 years. So that's the contact information. I'll be glad to take questions. Yes?
As far as the OEMs go, there would definitely be engineering changes to subcomponents from other suppliers. I don't know if this is just a total replacement part. There's going to be some sort of design. Definitely have to go through OEMs.
Yeah.
Go through tier 1. So looking at the investment goes straight to Volkswagen, BMW, because they're going to send the engineering change down to their tier 1 suppliers, and tier 1 will send down to their 4. So.
Right. Yeah. I'm going to let the people who have worked with the auto industry more than I have answer that. You may want to speak into the microphone also. Sorry.
I was just going to say, yes, you ultimately would have to sell it to a tier 1, but the tier 1 would basically provide the specifications form, size, and then the power modules would have to be defined in relation to the power and the current, but you could put what power modules you wanted to in that inverter that the tier 1 was buying from the tier 2. I mean, the OEMs was buying from the tier 1. So it is not a drop-in replacement. You are correct, though.
Yes.
I'm sure you presented a problem in this David. What makes this a disruptive?
Because if this got into the marketplace, everyone would shift to it. So the question was, what makes this a disruptive technology? I mean, I think that the advantages, the benefits to this, why would anyone not take it? Is that what you guys would say?
I'm sure you presented a problem in this David. What makes this a disruptive?
Just to say, yes, you ultimately would have to sell it to a tier 1, but the tier 1 would basically provide the specifications form, size, and then the power modules would have to be defined in relation to the power and the current, but you could put what power modules you wanted to in that inverter that the tier 2 was buying from the tier 2. I mean, the OEMs was buying from the tier 1. So it is not a drop-in replacement. You are correct, though.
Yes.
Well, I would say that it's a whole lot higher power density. It's a smaller package. It enables double-sided cooling. It's cheaper. So there are a lot of advantages. If it could be, it would have to be redesigned into a power module. I mean, not by power module, I mean an inverter or a converter or a charger from the ground up. But it's disruptive in that it could result in a whole lot smaller volume and size of these components.
Thank you very much.
All right, yeah, thank you.